In this lesson, we're investigating electrolytic cells. Our lesson objectives: identify features of an electrolytic cell and differentiate between a voltaic and electrolytic cell. Unlike the voltaic cell, which was spontaneous, the electrolytic cell is non-spontaneous, meaning it's going to require energy, and this energy from a power source like a battery must be supplied to move the electrons from the anode to the cathode. And when it does that, it's going to convert that electrical energy from the power source back into chemical energy stored in the battery. And so your rechargeable battery in your phone, for example, will function as both a voltaic cell and an electrolytic cell. When you're using your phone, we're using that battery that's functioning as a voltaic cell. But when you charge that battery, so rechargeable batteries will function as an electrolytic cell when we're recharging them. In this case, we're using a power source to move electrons from the anode to the cathode, or using that power source to convert the electrical energy back into chemical energy in the battery, so then you can use your battery again. So one application of this electrolytic cell process is called electroplating. And electroplating is the process of layering one metal on top of another. For example, when we want to plate jewelry. So this is gold-plated jewelry, underneath is another metal, and we layered the gold on top of it. Or how we chrome bumpers is another example. And so this is the process of electroplating. The battery here is going to force electrons to travel from the electrode, in this case a silver electrode, which is our anode. Remember, electrons always flow from the anode to the cathode. So it's going to force electrons from the anode, the silver electrode here, to our cathode, which is going to be the spoon. And so since we're dumping a bunch of negative charges onto the spoon becomes negatively charged, and it's going to track the silver ions in solution, which will reduce onto the spoon and form solid silver ions. So let's look at each half reaction separately. So remember, electrons always go from the anode to the cathode. So the silver electrode is my anode. Recall anox red cat, so the anode is a site of oxidation. So these atoms, these silver atoms, are going to, as we see here, Ag0, are going to oxidize and lose an electron and form this silver ion, which is going to dissolve in solution. So the silver atoms are turning to ions, and these ions are then going to be used to plate our spoon. And so the overall mass of this electrode is going to decrease as these atoms turn into ions. At the spoon end, these negative electrons are going to attract the positive ions from solution, and they're going to reduce and form, as you see here, they're going to form solid silver, our Ag0, on our spoon. And that's how we plate the spoon with, in this case, silver metal. And so since we're plating it with more atoms, the overall mass of the spoon is going to increase. Now this is not a spontaneous process like we saw in our previous lesson on voltaic cells. So the battery is used to force the electrons to the cathode. And so since electrons are going to the cathode actually has a different sign for electrolytic cells. It's actually going to be negative, and the anode is going to be positive. And again, that's why we have the battery. It's why we need it. We need the battery to force electrons to this negative electrode, or this negative cathode. So another application of the electrolytic cell is the electrolysis of water. And water or other solutions can undergo electrolysis and be broken apart back into their pure elemental state. So for example, if we take liquid water and we use this process of electrolysis, we can decompose it back into hydrogen gas and oxygen gas. And so I assigned the oxidation numbers up here. You can see what happens is that the H+1 is going to reduce by gaining electrons, and the oxygen, the O-2, is going to oxidize by losing electrons. So the H+, which is here, is going to reduce, and this is going to be the cathode, and the O-2 is going to oxidize, and this is the anode. Again, it's always anox red cat. So the anode is always going to be the site of oxidation, which means a loss of electrons. And you can also see here, if you look at the coefficients, we have a 2 in front of the hydrogen and a 1 in front of the oxygen. So we are producing twice as much hydrogen gas as oxygen gas. And you can see that here in the chamber. You can see there's roughly twice as much hydrogen gas being produced as oxygen. So let's check your understanding. Can you identify features of an electrolytic cell? Now lastly, let's compare and contrast the voltaic cell, our battery, and our electrolytic cell. So what is similar is going to be listed in red here, and then what's different is going to be listed in blue. So for the voltaic cell, our battery, electrons flow from the anode to the cathode. Same thing for the electrolytic cell. That's always the same. And what's always the same is also anox red cat. So the anode is the site of oxidation, and the cathode is the site of reduction. Now, putting another way, the anode is the site of the loss of electrons, and the cathode is the site of the gain of electrons. Okay, what's different? Well, remember, in the voltaic cell, it's a spontaneous reaction. We use table J to see which metal is going to oxidize more readily. So it doesn't require any outside energy source. We're going to make electricity, so we do that by converting the chemical energy of the reaction into electrical energy. It also has a salt bridge, which we can see here, and the function of that salt bridge is to allow for ions to flow and keep the cell neutral. Lastly, the anode is going to be the negative electrode, and the cathode is going to be the positive electrode. And that makes sense because the electrons are being pulled spontaneously towards the positive electrode since they are negative. For the electrolytic cell, it is not spontaneous, so we do need outside power source like electricity. And so what it's going to do is going to take that power, that electricity, and convert it back into chemical energy. Notice there's no salt bridge in the electrolytic cell, and it's an easy way to identify it. And the difference in terms of charge is that the anode is going to be positive in the electrolytic cell and negative for the cathode in the electrolytic cell. Let's check your understanding. Can you differentiate between a voltaic and electrolytic cell? At this point, you should be able to identify features of an electrolytic cell and differentiate between a voltaic and electrolytic cell.